Hello friends, now let us see the previous year gate questions which appeared on the topic, that is diode capacitances. The theoretical session I have already taken in my previous videos. So let us see the first question. Which of the following statement is false for adjunction diode? The depletion capacitance increases with increasing reverse bias. Remember the depletion capacitance, if you remember, that was what? Depletion capacitance is nothing but the capacitance across the depletion layer, that is eta, that is epsilon A by W, if you remember the expression. So capacitance, I'll go directly in the solution part so that you can understand the relationship between the biasing voltage and the capacitance. The transition capacitance, that is depletion layer capacitance of a diode, is given by, you can see the relation, that is what you have, epsilon A by W. So here epsilon is what? That is permittivity. Epsilon is permittivity, A is area of cross section of the junction, W is width of the depletion layer, and width of the depletion layer is given by, we have already derived this expression, to epsilon by Q into 1 by Nd plus 1 by Na into Vj. So from this expression we are able to understand that your W is proportional to root of Vj. Vj is what? That is V naught for no biasing voltage. This is V naught minus Vs for forward bias voltage, and V naught plus Vr for reverse bias. Fine. So when it is forward biased, so biasing voltage is Vf. Fine. So when it is reverse bias, biasing voltage is Vr. Just to let you know, so capacitance will be definitely inversely proportional to what? The width of the depletion layer. So I have put that expression here in the expression of capacitance. Fine. So it is clear from the above equation that depletion layer capacitance decreases with increase in the applied voltage, reverse biasing voltage. Fine. So if you see the answer A, the depletion layer capacitance increases with increase in reverse bias. Is it true? The depletion layer capacitance, you can see here, that decreases with increase in the reverse bias. Fine. So now second point, you can see the diffusion capacitance. The diffusion capacitance is given by, you need to remember this, we have already derived that expression where tau id eta Vt, tau is average lifetime of minority carriers. In which region? That is in N region, minority carriers in the N region, right? In N region. So ID is the diode current, Vt is the thermal voltage. So you can see the forward biasing current of a diode is given by, that is the relationship we have already seen many times, not only once. So I'll replace this at the rate. It's not at the rate, rather it is almost equivalent to this. So that is the relation you have. V is forward biasing voltage across the diode. So, and remember, this is forward biasing. It can be positive for forward biasing and negative for reverse biasing. And this H is not, basically this is ideality factor. It's not H, it's basically that ideality factor we discussed. Fine. So diffusion capacitance is given by this relationship. So here, so this is the relationship. What I find, the diffusion capacitance is directly proportional to the exponential relation with the forward biasing voltage of the diode. That is the relationship you have. So now if you see, the diffusion capacitance is function of forward biasing voltage, and your transition capacitance is also function of biasing voltage. So diffusion capacitance is also known as the storage capacitance. So what we find in case of forward biasing, diffusion capacitance is much larger. In case of reverse biasing, this will play the role. So now let us see the options here. The depletion capacitance increases with increase in reverse bias. That's not correct. We have seen the depletion capacitance decreases with increase in the reverse bias. That's true. That's your second. Then diffusion capacitance. Now see this depletion. This was depletion. Diffusion capacitance increases with increase in the forward bias. This is also true. You can see from here, when you apply the forward bias, the diffusion capacitance is increasing. So that option is also correct. B and C are giving me the correct option. The diffusion capacitance is much higher than the depletion capacitance when it is forward bias. That is also correct. So you have to find the false statement. This is true, this is true, this is true. The false statement is A. So I'll just make correction because we have to find the false statement rather than the true. So answer is A. Option A is false. All other options are true, correct. So now let us see the next question. The depletion layer capacitance CT of an abrupt PN junction. Remember the relation I discussed this was also for abrupt PN junction. So for abrupt PN junction, what is the relationship? CT is directly proportional to minus of VR under root. You can see from here, if you neglect V naught, CT is inversely proportional to VR root. So if it is inversely proportional, it becomes minus 1 by 2 here. So your answer is C. Now let us see the next question. Just I have explained and derived that expression to come to a conclusion. Otherwise, that is your direct answer. Now let us see the next question. Consider an abrupt PN junction. Let VBI be the built-in potential of this junction and VR be the reverse biasing voltage. If the junction capacitance Cj is 1 picofarad for VBI plus VR of 1 volt, then you have to find the junction capacitance when VBI plus VR is 4 volt. And we know what is the relationship between junction capacitance and reverse biasing voltage. That is what you can see, that was Cj is inversely proportional to V0 plus VR minus 1 by 2. So you just put that relation here. I get Cj2 by Cj1 equal to what? You simply change VR2 and VR1 here. So you are given V0 plus VR1, V0 plus VR2 are given to you 4 volt. This is 1 volt. So you get Cj2 directly. Fine. So that was simple relationship. Question was in 2004, 2 marks. Now let us see the next question. A silicon PN junction diode under reverse bias has a depletion region of 10 micrometer. The relative permittivity of silicon epsilon R is 11.7 and the permittivity of free space is given to you. The depletion layer capacitance of the diode per square meter. So depletion layer capacitance is given what? Epsilon A by W, that you know. We have already derived that expression. I have already given that relationship earlier as well. Fine. So you are given the different parameters here. If you have to find the depletion layer per unit area, so that is your depletion layer, depletion capacitance, depletion layer capacitance per unit area, that is CT by CA. So that is what? Epsilon by W. That is what you have to find. So you are given width of the depletion layer is given, epsilon R is given, epsilon naught is given. So you just put those values here, you get the answer. CT by A is nothing but 10 microfarad per meter square. Fine. Now let us see the next question. Compared to PN junction with NA and ND, that is stands for 14 per centimeter cube, which of the following statements is true for PN junction with Na equal to ND equal to 10 to the power 20? So what you have done, you have increased the concentration of the impurity atoms on both sides. So let us see what will happen to reverse breakdown voltage will lower, depletion layer capacitance is lower, reverse breakdown voltage is higher, depletion layer capacitance is lower. So let us see the effect on the reverse breakdown and this. Fine. When you increase the concentration on both sides, the breakdown voltage definitely decrease. But let us see this effect on capacitance. So depletion layer capacitance is nothing but, you know, that is CT. Fine. So and it is inversely proportional to W. So we know it is when you increase the reverse biasing voltage, W will increase and capacitance will decrease. So that's your conclusion. When impurity concentration increase, the depletion layer width reduces. I'm sorry, you have increased the depletion layer. You have increased the donor and acceptor concentration from what? From 10 to the power 14 to 10 to the power 20. So you have increased acceptor and donor concentration, and when acceptor and donor concentration are increased, W will decrease, and when W decreases, the capacitance will increase. So this is sure that transition capacitance will increase. So you can see from here, it will not, the answer is going to be from C and D, and answer is C. But let us see, when you are increasing and D, what has happened? W has reduced, and when W reduces, the electric field in the layer will increase, and when electric field in the layer increases, the breakdown voltage will reduce. That is the fact you need to remember. When electric field in the depletion layer increases, the breakdown voltage of the junction will decrease. Now let us see the next question. The built-in potential of an abrupt PN junction is given, that is 0.75 volt. Its junction capacitance Cj at reverse bias is reverse bias of 1.25 volt is 5 picofarads. You have to find the junction capacitance when reverse bias voltage is increased to this level, that is 7.25 volt. That was 2-mark question in GATE 2015, and we know that is the junction capacitance given to you. That type of question we have already solved earlier. So we have solved such type of questions. So we know Cj is inversely proportional to root of what? V naught plus Vr. So you are given the different conditions here. Vr is being changed from 1.25 volt to 7.25 volts. So you get the answer. We have already solved this type of questions earlier. Fine. So this is giving me the direct answer. Now let us see the next question. As shown, two silicon abrupt PN junction diodes are fabricated with uniform donor concentration ND1 and ND2 of this much. Fine. In AND regions of diodes. So you are given donor concentration of two in AND regions of the diodes. The uniform acceptor doping concentrations are also given to you, that is Na1 and Na2. Fine. So first diode has lower concentration, second diode has higher concentrations in P region of the diodes. Assuming that the reverse bias voltage is much greater than the built-in potential, the ratio of capacitances you have to find between capacitance and donor concentration. So let's obtained. So here we know that is your junction capacitance. We have already seen. There is nothing to talk about it again and again. We know the depletion layer width. So you are given these parameters ND and Na. So Cj is basically inversely proportional to this. So what I do, I will be simply putting -1/2 here. Fine. Na and Nd for two diodes are given to you. So I'll take the second diode and first diode here. So Na2, Nd2, Na2, Nd2 and Vr2. So I get the ratios. Reverse bias is same for both. So just by putting these values, I get relationship between the junction capacitances of two diodes. So this is all about the questions which appeared on the junction capacitances. What I observe here is, this is the second important topic after your depletion layer width. Many questions have appeared in GATE exam from the junction capacitances, and maybe at later stage there may be question on diffusion capacitance. Most of the questions are but on that is transition capacitance of the diode. So just wait for my next video for more GATE questions. Thank you.